All right, hello everyone. Welcome to discussion 4. Most of you have already seen the first half of this and we'll skip forward to the ending. My Wednesday section, this is the entire discussion for you. So I'm going to just go ahead and hop right into it. So I'm going to be working on my iPad. When I taught it in person, I worked on the document camera, but I can do just the same via my iPad. So give me just a second to switch on over. Okay, so hopefully this is working. Normally on Zoom, you can just share your iPad or iPhone via AirPlay, but AirPlay does not want to work on my laptop or on my iPad for some reason. So we're gonna try it this way. All right, awesome. So here is our discussion for updated worksheet. If you are still seeing the old one, go ahead and head to modules and you can find this updated one there. So let's go ahead and begin. So I am going to kind of color code as we go through this. So feel free to color code along with me, but definitely don't feel pressure if you do not have colored pencils or pens. All right, so this first part of the discussion worksheet, we're doing some anatomy actually. So we're looking at the structures of a neuron. After this, we'll hop into the actual physiology, but I wanted to start with some anatomy first. So first we have structure A. So A is known as the soma, AKA the cell body. So this is where we integrate stimuli or integrate information. That is at the soma or the cell body, containing like the nucleus and the important decision factors of the neuron. B is the dendrites, and dendrites are responsible for receiving signals. So they have these long arm structures and they will receive signals. And what we see is those signals are normally neurotransmitters. So they'll pick up neurotransmitters, send them to the cell body. The cell body will integrate them, and then we will decide if they are strong enough here at the axon. So, or sorry, the axon hillock. So structure C is the axon hillock, and it is this structure right here, and it's the beginning of our axon. And axon hillock is associated with threshold. So if the stimuli is strong enough, if the cell body decides that the stimuli is strong enough, it will reach that axon hillock and be sent down the axon. So here, structure D is our axon. So axons are responsible for sending signals. So we send this signal or stimuli down the axon. And as you see in this specific neuron, this axon is coated with cells. You can see that we have these cells coating the neuron, and those are called myelin cells, and together they form the myelin sheath. If the neuron is myelinated, that means we're going to have a really quick impulse sent down that axon. That signal or stimuli will be sent down very quickly compared to an unmyelinated axon. And in just a little bit, I'm going to show you a video of this occurring. And then lastly, we have F, and F is known as the axon terminal. And this is where we will release neurotransmitters. So again, the dendrites will receive the neurotransmitters or the signal. The cell body or the soma will integrate it. If it's strong enough, it will be sent past the axon hillock down the axon. If the axon is myelinated, that signal will travel very quickly, and it will reach the axon terminal, which will release neurotransmitters, which will cause that kind of action. All right, so now that we're done with the anatomy, before we hop into the true physiology, I wanted to go over the 3 different types of channels that you definitely want to be familiar with. So in unit 1, we learned that channels are openings on the cell membrane to allow for the passage of ions and certain molecules, but we didn't discuss the actual types of channels that there are. So we're going to go over 3 of them today. There aren't just 3, there are more in the body, but these are the 3 that you definitely want to be familiar with. So let's go ahead and start with our ligand-gated channels. So our first channel is called a ligand-gated channel. So how these channels work, and one other thing that I wanted to do is, I forgot to mention this, just point out what we're looking at here. This is going to be considered the ICF, and this is the ECF. So anything on this side is ICF, anything on that side of the membrane is the ECF. And this first side is showing a closed channel. So you can close the channels over on this side of the picture. And this side is showing an open channel. So we're going to kind of go over how we open the channels. So back to our ligand-gated channels, we're going to go ahead and use the molecule sodium in all of these examples because sodium is a very commonly used molecule in the body. And so we'll just go ahead and use sodium. One thing we know is that sodium exists in higher concentrations outside of the cell in the extracellular fluid. And when we need to move it inside of the cell, we have to use a channel. So it can't just simply diffuse past that cell membrane. We have to open and channel. And if we use a ligand-gated channel, what we see is that we have some type of neurotransmitter that will be released. Sorry, changing colors here. We'll have some type of neurotransmitter be released that will bind to this ligand, this receptor on the cell membrane, and cause that channel to open. So ligand-gated channels work by neurotransmitter binding. So when a neurotransmitter binds, we see that that ligand-gated channel will open, and therefore sodium can move into the cell. So that's how our ligand-gated channels open. A ligand is a receptor, and we have these ligand receptors on the cell membrane. We'll release some type of neurotransmitter from an axon terminal that will bind to that ligand, and it will cause that channel to open. So once that channel is open, our ions can go ahead and move through. All right, cool. So that was our first type of channel. Now we're going to move on to our next channel. The color I want is not there. I'll use this one. So our next channel is called a voltage-gated channel. Voltage-gated channel. So this deals with changing the voltage of a cell. So again, we have sodium outside of the cell in higher concentrations, but since sodium is a charged ion, we can't simply just diffuse it past the cell membrane. We do need to open that channel. So we can see that one way we will do this is through changing the voltage or the electricity inside of the cell, so making the cell more positive or negative. So most cells are at rest at -70 millivolts. Just associate that with the cell at rest unless it's otherwise stated. We will use an example soon where it is stated that the cell is at -45 millivolts at rest, but in most cases, the cell sits at -70 millivolts when at rest. In that example, we will also see why we have a change in voltage. We're not going to go into it yet, but just for now, think about having some type of change in voltage. So let's say we go to 30 millivolts. So when we have a change in voltage, that will open up a channel. So when the cell voltage becomes more positive, or we have some type of change, that will open up that voltage-gated channel, and that ion can now flow into the cell. So we see our voltage-gated channels work by a change in voltage. Sorry, my handwriting is so bad on my iPad. I guess I need a better pen than the $5 one that I got at Goodwill. But yeah, there's one other thing that I want to add here, and you can just mark this down to like -90 millivolts. Once those ions, flow in the cell, we'll have some type of process that will eventually bring the cell back to a more negative state. So just for illustration, when you return to looking at this, once we've completed this whole worksheet, this is a good kind of reference to have on there. It's representing hyperpolarization, but we aren't there yet, so don't worry about it yet. So the last example of one of the channels we have is a mechanogated channel. Mechanogated channel. We don't go too far into these in this discussion worksheet. We'll see it in discussion worksheet 5, but overall, we don't hit these too hard compared to the ligand-gated and the voltage-gated channels. So we have our ion outside of the cell. It can't just simply diffuse in. So with our mechanogated channels, which we find mostly in like skeletal tissue, there will be some type of physical stretch of the membrane itself, and this will cause those channels to open. So a stretch or some mechanical deformation of the membrane itself will cause that channel to open, and the ion or the sodium in this case can move into the cell. So we see physical stretch will open the mechanogated channels. All right, awesome. So I wanted to add one more note here before we move on. So when looking at our ligand-gated channels, what we see is these are most commonly found. Our ligand-gated channels are most commonly found at the dendrites and cell bodies. Sorry, my color coding's off. The voltage-gated channels we see at the axon hillock and axon. So I made a small color coding mistake. So I did want to color code the ligand-gated channels in this color to go as a different shade of this. And then I wanted to color code the voltage-gated channels in this color to go along with that. So sorry, I made a little color coding mistake there. If you want to change your colors, go ahead and do that. I'm sorry about that. All right, so now that we have this information, let's go ahead and move to the next page where we will answer these two sets of questions. But before we do that, we're going to work through this example that I added. So what we're looking at here is two neurons. Normally neurons neighbor each other and send signals to each other until it reaches the brain. So I'm going to show y'all just a picture of one of the longest neurons in the body. Oh wait, it's on my computer. So let me see. All right, awesome. So I got this pulled up. So this is an example of one of the really long axons in the body, actually the longest, and it's the sciatica. So you can see it extends all the way down to the base of the foot, all the way up to the hips. So you can see the axon, how long it is, the dendrites, how far they extend, and yeah, some of the axons and or neurons in the body are extremely long. So that just kind of gives you an example. Some of them are really short, but some are also very long. Okay, so moving back to our worksheet, let's go ahead and continue on with this example. So a lot of neurons connect with each other. The other neurons in the leg normally form these chains and don't extend throughout the entire leg. So this is kind of what we're looking at here. So we have our first neuron, and again, how neurons communicate is through neurotransmitters. So what we see is that from the axon terminal of our first neuron, we're going to release neurotransmitters to the dendrites, the receivers of the following neuron in that chain. And remember, on the dendrites, we have these receptors called ligands, and ligands receive those neurotransmitters and open up ligand-gated channels. So along the dendrites, we will open up these ligand-gated channels. We will also open up some on the cell body, but mostly the dendrites are the ones opening up the ligand-gated channels. So we'll go ahead again and use sodium as our example here. So we have sodium outside of the cell. And once we open those ligand-gated channels, sodium can now flow into the cell. So this specifically is called a ligand-gated sodium channel. So once we open those ligand-gated sodium channels, sodium can flow into the cell. And when sodium flows into the cell becomes more positive. So the cell body becomes more positive because sodium has a positive charge. And so once this occurs, that positive charge will reach the, did I just color code this wrong again? I think I might have made a color coding mistake, but it's all right. So once that sodium, or once those ligand-gated channels open, I believe that I meant to color code these again in this color. Once those open, and now from now out, my color coding is correct, we see the opening of voltage-gated channels. So we open up voltage-gated channels. And so we see that these exist along the axon and at the axon hillock. Again, we're working with sodium, so we call these voltage-gated, I guess I'll write it all out. We call these voltage-gated, which can be abbreviated VG, voltage-gated sodium channels. And so we opened those because the cell became more positive. It became positive enough to reach the threshold at the axon hillock. And we opened up these voltage-gated sodium channels along the axon. So with myelinated axons, we see that that impulse jumps in between the myelin cells. These spaces in between the myelin cells are called the nodes, specifically the nodes of Ranvier. And I'll write that out in just a little bit. But what we call this jumping action from node to node, the impulse jumping from node to node, is called saltatory conduction. Saltatory conduction. If we did not have a myelinated neuron, we'd have to open many more voltage-gated sodium channels along the axon, and that would take a lot longer. This saltatory conduction lets that impulse hop from node to node, just like telephone lines are insulated, and signals and impulses can be passed from line to line or box to box. Same thing with saltatory conduction. So I have a quick video just to illustrate this. All right, so one other thing is that conduction and propagation kind of go together.
When an action potential in an axon spreads to a neighboring region of its membrane by a series of small steps, the process is called continuous propagation. When it propagates by jumping from one site to another along the axon, the process is called saltatory propagation. Saltatory propagation occurs along axons that have myelin sheaths. In the peripheral nervous system, these myelin sheaths are formed by Schwann cells. The myelin acts as an electrical insulator, allowing ions to move across the cell membrane only at the gaps or nodes between adjacent Schwann cells. Therefore, action potentials rapidly travel from node to node.
Okay, awesome. So hopefully the audio wasn't messed up there. I don't know if it picked up audio from my iPad or if it picked up audio.
Now that we know how a signal can...
I'm not sure which the audio picked up, but the audio isn't that important. I kind of wanted to show you what it looks like. Okay, cool. So before we add anything else, I wanted to go ahead and start on this graph that I have below. So here's when we're actually going to discuss those voltage changes. So we'll start by labeling our voltage, which is in millivolts. So up here, we will do positive 90 millivolts. Then we will do around right here, negative 55 millivolts. It's obviously not spaced out super correctly, but for what I need to illustrate, I need a little more room. Here, we'll do negative 70 millivolts, which again, that normally means that the cell is at rest unless otherwise stated. And down here, we'll do negative 90 millivolts. So threshold is negative 55 millivolts in most cells. I'm pretty sure it's all cells, but unless otherwise stated, threshold is negative 55 millivolts in most cells. So what we see is that whenever a cell is at rest, it's sitting at about negative 70 millivolts. And now I'm going to actually use the correct color I meant to use before. So once we start opening those ligand-gated channels, we see this kind of stair-stepping action up to our threshold point. So whenever that sodium is coming in through those ligand-gated channels, we're making the cell more positive until the millivoltage reaches negative 55. So going from negative 70 up to negative 55, that means it's becoming more positive. So once we hit negative 55 at this threshold point right here, our axon hillock, what we see is this rapid influx of sodium, like it's kind of just been leaking in, but then all of a sudden we have this rapid influx of sodium down the axon. So we have this, sorry. I'm having all types of problems here today. Sorry, y'all. Returning to this. So we have, so once we open those voltage gated sodium channels, we'll see this rapid influx of, sodium down the axon. Sorry, I got a little off by a phone call, but let me go ahead and label this out for you. So this stair-stepping action in purple should be this ligand-gated, representing these ligand-gated sodium channels opening. So this can be ligand-gated sodium channels open, increasing the positivity of the neuron or of the cell. And then once we have this rapid influx, that is because the voltage gated sodium channels open. So what we call this is depolarization. So depolarization, and again, that's caused by the voltage gated sodium channels opening, and cell increases positivity. So we have that influx of sodium into the cell, down the axon, and that is what causes that that rapid rise in positivity or of voltage. So we depolarize at up to, I don't know why I wrote positive 90. It should be positive 30, about positive 30 to positive 40 millivolts. And then what we see is that we will have a decline in a decline in the voltage. And we'll come to that now. So what we see is that whenever, and I'm actually going to color code this in purple. How am I going to color code this? No, I'll keep it in. I'll do it in dark blue. So what we see is that we have this decline in voltage. And that decline in voltage is caused by the opening of potassium channels along the neuron. So we open potassium channels along the neuron. So these are voltage-gated potassium channels. And when we open those, we see potassium flows out of the cell because potassium exists in higher concentrations inside and is going to flow with its concentration gradient to outside of the cell. So what we call this is repolarization. So the cell depolarizes up to about positive 30 or 40 millivolts, and then it repolarizes due to voltage-gated potassium channels opening and cell decreases in positivity due to that K plus that potassium outflux. All right, awesome. So once we open those potassium channels, normally we see this process where potassium continues to flow out of the cell past rest. So here is our resting point, and potassium kind of flows out continuously, a little bit more than the resting state. So what we call this is hyperpolarization. And it's just kind of the outflow of potassium past rest. And this is kind of to give the body a break. For example, if this was like the cardiac cells, like cardiac cells don't work through neurons for sure, but they also are depolarized and repolarized. Same with skeletal tissue. You know, when you contract your muscles, that's because the muscle cells are depolarizing. When your heart beats, it's because your cardiac cells are depolarizing. And so you need a little bit of a break before you depolarize again. And so that hyperpolarization just kind of adds some time to get back to that threshold. So at rest, we only have to move, in this case, 15 millivolts to hit, threshold and depolarize. Hyperpolarization makes you have to move negative or, move up 35 millivolts. So it just adds some time in between contraction or stimuli or whatever area of the body we're talking about. So, once we hyperpolarize down to about -90, we will either have another set of, depolarization, or we will return to rest. So what we see is that once that voltage-gated sodium channel, opens and we have this depolarization, I forgot to add this right here at about this point. I'm going to change it to this color right here. What we see is that we will open up these voltage-gated voltage-gated calcium channels. So here is voltage-gated calcium channels. So calcium, which exists in higher concentrations outside of the cell, will flow into the axon terminal. And when this occurs, we will see exocytosis of neurotransmitters. So exocytosis, the release of neurotransmitters. So that influx of calcium into the axon terminal will cause exocytosis of neurotransmitters, so they will be released to the next neuron. All right, so these are very important processes to kind of understand. Before we go ahead and answer these questions, I did want to return back up here to our graph to add some more things. So the stimuli to open our ligand-gated sodium channels is not always strong enough. Sometimes we don't always release release enough neurotransmitters to open, enough, ligand-gated receptors along the cell. And it can look kind of like this stepping up, not reaching threshold, and then step back down and step up until we have a strong enough stimuli, and then, hit threshold and depolarize. So what we call the stepping up right here, we call that an EPSP, excitatory postsynaptic potential. Excitatory postsynaptic potential. So that's kind of that increase in positivity, increase in voltage. This decrease right here is called an IPSP, inhibitory postsynaptic potential. It inhibits the graded potential from being strong enough to reaching an action potential. So if you want to draw this out, anything above this line is kind of referred to as the action potential. So action potentials kind of occur at the axon and at the axon terminal. They travel down the axon and axon terminal and then cause the release of neurotransmitters. Above this line, we have graded potentials. So here we have graded potentials. And what we see is that graded potentials must be strong enough to cause an action potential. So EPSP and IPSP are parts of a graded potential. And so a way you can think of a graded potential is the sum of our excitatory postsynaptic potentials plus our inhibitory postsynaptic potentials. So that's kind of what makes a graded potential, is the sum, is the EPSP strong enough or stronger than the IPSP? It's kind of the sum of those until we, can reach that -55. So an example of this would be like if a bee lands on you. If a bee lands on you, it's a heavy enough creature to, be detected by your receptors in your skin to reach this -55. We'll have depolarization, and that signal, that action potential will be sent to our brain, and we will, integrate, hey, a bee landed on our arm. However, a mosquito is really small, and kind of gross fact, when a mosquito lands on you, it actually vomits on you first. And that vomit contains numbing receptors that numb the skin. And so the mosquito can land on you and bite you a few times before you feel it. So that's kind of like this, not strong enough. So we bring our voltage back down. And then eventually those numbing agents kind of start to wear off, and we start to feel the mosquito biting us. And then we eventually reach that -55 millivolt threshold, and we have an action potential and look down and see that a mosquito has been biting us, and we hit it, and then we see that we've already been bit a few times. So graded potentials have to be strong enough to cause an action potential. The two components of our graded potential are the EPSPs and the IPSPs. All right, awesome. So now that we have all of this labeled below, let's go ahead and answer our questions. So first, we're going to look at our voltage gated channels, which again should be in this, purpley color. And then we're going to look at our ligand gated channels. So let's start answering. So put these ion channels, and again, we're looking at ion channels in the correct locations of the neuron. So those spots on the neuron. So where do we see voltage gated sodium channels? We see voltage gated sodium channels at the dendrites and the, you want to write primarily dendrite, or sorry, just got a little ahead of myself there. We see the voltage gated, sorry, this color coding has messed me all up, at the axon hillock and the axons. So axon hillock and axons. Voltage gated potassium channels, we also see them at the axon hillock and the axons. Voltage gated calcium channels, we see at the axon terminal. So that's where we see our voltage gated channels. And again, you know, we kind of pointed that out here. All right, cool. And I color coded this wrong again, didn't I? Yes, I did. Sorry, when I did this on paper, it went very smoothly. My color coding is, I don't have my answer key in front of me. I'm just doing this from memory. So my color coding got kind of messed up. So our voltage gated channels, we put them in blue, and our ligand gated channels we're putting in this purple color. So where do we see our ligand gated sodium channels? It's going to be mainly at the dendrites and some on the cell body or the soma. Our ligand-gated potassium channels are mainly going to be seen at the dendrites. We didn't really go into potassium ligand-gated channels. They didn't fit this example, but they are seen at the dendrites mainly, and then also at the cell body. And then lastly, ligand-gated calcium channels. This is one of Dr. Chang's short questions. These are seen nowhere. We only have voltage gated calcium channels. So that's kind of one of those trick questions. So make sure you know we only have voltage gated calcium channels. All right, so we have now answered part B. So let's do C. C is asking us about these specific events. So we're first asked about EPSP and IPSPs, where these occur. Again, those are parts of the graded potentials, and we see that they occur at the dendrites and cell bodies, or the somas. That also is the case for IPSPs, the dendrites and soma. Our action potential occurs at the axon hillock and axon. Saltatory conduction occurs at that myelin, in between the myelin sheath. So if you were using the lettering from above, we'd say myelin, but specifically those nodes of Ranvier, those spaces in between the myelin cells. Continuous conduction in this example occurs nowhere, because this is a myelinated axon. So continuous conduction only occurs in unmyelinated neurons. And then lastly, exocytosis. Where does that occur? That occurs at the axon terminal with those voltage gated calcium channels. Okay, awesome. So this is the second part of your worksheet. So hopefully you understand this, worked through it a few times. Again, I apologize about the color coding error, but yeah. So now we're going to move on to the third part of this worksheet, the membrane potential. I know this question probably looks big and scary, but I promise you it's actually extremely easy. So what we're looking at here is some single-celled organism and some swampy canal. What we see is that it is stated that it has a resting membrane potential of -45 millivolts, and the outside fluid is 0 millivolts. So we took, some ion measurements, some concentrations below of the cell itself and the swamp. So what we are going to do is use the Ernest equation, which is listed here. It will always be given to you. You don't need to worry about memorizing the Ernest equation. And we're going to calculate the membrane potential for each. So again, the cell is, the inside. So cell is in, swamp is out. I don't know why it's doing that, but cell is in, swamp is out. So ion out, ion in. That's kind of what we're referring to there. So we'll start off with the membrane potential for potassium. So we take our equation 61 times log N, times log of the concentration in or outside, out over N. And what we get is, oh, I don't have my answer key with me. I think it's -65. I'm going to check before. Then we do it for sodium. So we repeat that same equation, log out, which is 175 over N. And we get our answer. And then the membrane potential for chloride, we do 61 times log out over N. And I know for sure here we get 0 millivolts. So let me double check these answers. Okay, awesome. So it was -90 millivolts for the membrane potential of potassium and 65 millivolts for the membrane potential of sodium. So that's all you have to do to calculate membrane potential using the Ernest equation. I did want to go over something else. So let's say we're trying to calculate the membrane potential for calcium. Our equation would look like 61 over 2, taking that to charge times log, ion out over ion in. Chloride, we didn't really need to do this because it was 40 over 40 giving us 0. But let's say it wasn't 40 over 40, we would take 61 over -1 times log, out over in. So that's what that Z is representing, just in case you were wondering. All right, so that is all I'm going to handwrite to you. So I'm going to go ahead and switch back over to my laptop to finish up this worksheet. How many minutes are we into this recording? I think I'm actually gonna let's answer this last one and then I'm gonna make a part 2. So when looking at the last part of this discussion, or this third part of the discussion worksheet, we're asked, based on our calculations, explain which cell membrane is most permeable to what ion, so when the cell stays at rest. So remember, it was given that the cell is at rest at -45 millivolts. And we see that with this, the cell will be most permeable to potassium when resting, because that -90 is closest to -45. So that's kind of how you can compare those two. The cell will be most permeable to the ion that it's closest to in voltage. Then we're asked, explain what's the biggest difference between the GHK and Ernest equation. So what we see here, the Ernest equation is here, the GHK is here. First of all, the GHK is way more complicated. And we don't do any calculations with that. We do calculations with the Ernest equation, so please know how to use this one. But the Ernest equation only calculates membrane potential based on ion concentrations in and outside of the cell, whereas the GHK equation considers the permeability of the cell membrane to each ion. So you'll go over that briefly in lecture, but that is the answer there. However, when doing calculations, we just use the Ernest in this class. You don't have to worry about the GHK equation and doing calculations with that. All right, so this recording has taken me a little bit longer than expected. So I'm going to go ahead and end it here and create a part 2 that I will be sending out in just a moment. Thank y'all.